Alright, physics students, we are going to be finishing off our work on the unit that we were working on at the end of last term. We got a bit disturbed by, no doubt, the things that you have seen already, the coronavirus and everything like that. So what we're going to look at is thermodynamics, which is the last thing that we need to look at. Now, thermodynamics, as you can see there, is the area of physics that studies the effects of heat, work, and energy on a system. Now, this, while it may not seem that important, does underpin a lot of different parts of physics. So it's important that we do understand how it works. It also has massive crossovers into chemistry, which is where I know it a lot from. So we're going to be looking at thermodynamics probably for the rest of this week, and then we will probably move on to our next unit. Now, in thermodynamics, we actually have 3 laws. Okay, now those 3 laws are rather confusingly put as the 0th law, the 1st law, and the 2nd law. For now, you don't need to worry about that, but just remember that bit of a weird quirk when we get to it. The 0th law is, we'll talk about a bit later. The 1st law you may already know because I've started to write it just over there. Okay, I'm sure many of you can finish that in your head, but the law of conservation of energy states that energy can neither be created or destroyed. Okay, and that is a very important law, and it helps to explain the 0th law, which we'll talk about probably in our next lesson. Basically, a few other definitions that we have to go over. Heat is energy that is in the process of being transferred from one place to another. And work is energy that is being transferred due to the action of a force. Please put these 4 definitions. Please put these 4 definitions in your notes, okay, as they'll be important for later. Now, something very interesting that I want to talk about today is the fact that you cannot feel temperature. You cannot feel the temperature of something, okay? When you feel something and you think, oh, that's hot, what you're actually feeling is the transfer of energy, okay? So to do this, we can try this in a very simple way. What I want you to do is I want you to get three, they can be bowls, they can be dishes, basically anything that can fit a bit of water in, okay? In the first one, what I want you to do is I want you to put in some water. So water, that's cold water, plus a bit of ice, just to give it the icy coldness. Okay? In the second one, what I want you to do is put some hot water. Okay, now, this water should not be enough to scald you. It should just be warm to the touch, but not hot enough to burn you, okay? Please do not burn yourself while doing this, okay? So that'll be in your last one, and in the middle, what I want you to do is just some warm water. It doesn't have to be very warm at all, just a bit of hot water mixed with a bit of cold water, okay? Now what you're going to do is you're going to get one hand, and you're going to put it in the water plus ice. You're going to get your other hand and you're going to put it in the hot water. And what I want you to do is leave them there for a few minutes. Okay? You might want to pause the video while you do that. And then once you've put them in for 1 or 2 minutes, unpause the video and you can hear my next instructions. Alright. So, now that you've had your hands in the cold water and the hot water for a couple of minutes, I want you to take them both at the same time and put them in the warm water together. Okay? what kind of sensations are you feeling? Are both your hands feeling the same? Well, what I think you'll find is the hand that's been in the water and the ice is going to feel like this warm water you're in is hot. Okay? And the hand that's been in the hot water, when it goes into the warm water, is going to feel like it's cool. Okay? How do you get two different feelings from the same temperature water? Well, it's all about the energy transfer. Okay? Because your hand was in the cool water, it has lost a lot of its energy. A lot of the energy has transferred into the cold water. Your hand in the hot water, well, the hot water is hotter than your hand, so a lot of the energy has actually transferred back into your hand, making your hand warmer. So now, when you take both hands and put them in the warm water, one hand is receiving heat from the water, and the other is putting the heat into the water. So when we feel that transfer of energy, we actually see we actually get this feeling of hotness in one hand and coolness in the other. Okay? This is basically showing you that although we may feel like we know what temperature something is, it always depends on what temperature we ourselves are. We're only ever going to feel the transfer of energy. Alright, let's go move that down a bit now. Now, this also compares to things that we touch every day. For instance, if you were to pick up something metal, okay, things that we pick up that are metal often feel cool to touch. Things that we pick up that are made of wool or plastic often feel warm or just room temperature. That's all to do with how energy transfers between them, because metal is what we call a conductor. Let me just fix that out. Okay. Conductor, and wool and plastic are what we call insulators. Okay, and because of that fact, the insulators do not take energy very quickly from your hand, so it feels warm or room temperature. Whereas metal tends to take energy quite quickly from your hand, which makes it feel cool to the touch. Whereas when you originally touched both of the objects, they were the same temperature. That's a bit of a weird thing, where we often think metal things are cold, but they're not. They're just taking energy from our hand, which is why they feel cool. Basically, a lot of our knowledge of the transfer of energy comes from our basis in the kinetic particle model of matter. That is, that all matter is made up of little particles that are in constant motion. Okay, these particles are what we know as kinetic energy. So basically you've got these little particles, and they're constantly moving around all the time. Okay, the faster they're moving, the warmer we say something normally is. Okay, the more energy it has. Basically, this idea of heat energy can be basically taken back down to the idea of how much kinetic energy does this object contain. Okay, if they're moving really, really quickly, it's got a lot of kinetic energy, which means it's very warm. If it's moving really slowly, then it has very little kinetic energy, so it's going to feel quite cool. Okay? This also has impacts on our scale of energy. For example, on a thermometer, on a normal thermometer, we have like 0 down there. Well, at least in Australia we do. And you go all the way up to there. Okay, and maybe it might be 100 degrees up there. Now, is that where the temperature scale stops? No, not at all. You can keep going far, far above your thermometer. It's just 100 is boiling. That's where a lot of our lab thermometers end up. And 0 is pretty much the lowest temperature you'll get to in lab conditions. So that's basically where it stops on the way down. However, the temperature scale is not limited to a thermometer. In fact, the temperature scale, if we go in degrees Celsius, goes basically to infinity up there. You can always add more energy to something, although you do risk breaking those things at the time. But there is a limit to how much energy you can take from something. The lowest temperature that it's theorized that you can get to is negative 273.15 degrees Celsius. Okay, that's known as absolute zero or 0 degrees Kelvin. Okay, that's the temperature where you can no longer take energy from an object. It has lost all energy at all. Okay. Now, scientists have not been able to get there because obviously in order to take energy from something, you need to be able to have something that is, you need to have a way of transferring that energy away. And that is very difficult when you get to low temperatures because simply the energy in the environment around it can easily bleed back into it, ruining what you've done. But basically, it's theorized that at this temperature, all atomic movement, all of this movement of the particles will stop. There won't be enough energy to continue this kinetic motion. Okay, so this idea of kinetic energy and this temperature scale are very heavily linked. Okay, the more energy there is, the higher up the scale you are. The less energy there is, the lower down the scale you are. Okay. Now, so this means, of course, that when we look at our models of energy, our particle model, we can look at a solid, a liquid, and a gas. Oops. Gas, there we go. Alright, now in a solid, all the particles are quite densely packed together. Okay, I really should have drawn a smaller box. But particles are very densely packed together. They do in fact move around a little bit, okay, but they're quite restricted in how they are. Okay, so they're only able to move around a little bit, they bounce around, but are mostly locked in place. Okay, in a liquid, they are definitely more spread out. And this means that it's easier for them to move around. And they can move basically between each other. Okay? So in which solid or liquid do you think there's more movement? Well, the answer to that is definitely in liquid. In liquid there's more movement. And so if we link that back to our idea of the temperature scale, do you think solid or liquid would be further up the temperature scale, having more energy? If you said liquid, you're absolutely right. Okay, liquids have more energy. If we come to a gas, gases have even more energy, which means they're even further spread apart. Okay, and they move around quite rapidly. All right. They're constantly moving around, bumping into each other. They have the most energy out of these three different states. And so they would be placed even further up that energy scale there. These particles, however, do have some attachments to each other. For instance, in the solid, I said that they're mostly like they don't move around that much. Okay, it's because they've got intermolecular bonds that attach them to each other. This prevents them from moving much, and also stores a lot of the energy that is in those solids. Now, this idea of particles moving comes up a lot in diffusion. Hopefully you all know what diffusion is. But basically the idea is if you have a room and you say spray a bit of perfume in one part of the room. Now remember, a room is not empty, it's filled with oxygen and nitrogen, mostly nitrogen. So say we've got this perfume that's been sprayed in the corner. Eventually, people over here, that is a very bad head, people over here will be able to smell the perfume because the perfume gradually diffuses throughout the room. It starts spreading out from the one place. And that's because all of the particles are randomly moving, so even though you've sprayed it in one contained place, because they've constantly moved, they've gradually spread throughout the room. And so basically all energy can be put under two categories, that is kinetic and potential. Yeah, we talked earlier about heat energy actually falling under the umbrella of kinetic energy. Well, in fact, a lot of them do. You have heat, okay, that's a movement of the particles themselves. You have sound, which is the movement of energy through particles. Air particles normally, can be other objects as well. We have mechanical energy, where most people assume kinetic equals mechanical. However, basically sound and heat can also be taken down to basically that movement of particles. Electrical energy is actually the movement of electrons, okay? Therefore, it's a type of kinetic energy. And you also have radiant or light energy, which is actually the movement of photons, which are incredibly light particles, but they are particles nonetheless. And then you have potential energy, where you've got things like chemical, nuclear. You also have gravitational, and you also have elastic. Okay, all those basically come under the two umbrellas, kinetic and potential. Potential just means that the energy is stored, it's not actively being used, whereas kinetic is usually, there is usually a transfer of energy going on at the time. Okay, now energy can easily transform between potential and kinetic. For example, you can use mechanical energy to lift up an apple, turn it into gravitational energy. You can take a nuclear atom, you can release the energy in the atom and turn it into heat and light energy. Okay, both are very easy options. And you can also turn these into other types. For example, electrical energy can easily be turned into heat energy, and into sound energy, and into mechanical energy, and into radiant energy, which is how we do most of our life. In fact, some of the easiest ways to turn to get electrical energy are to turn chemical energy and nuclear energy into electrical energy. Bit of a sidetrack there, but you can see that you can basically turn any type of energy into any other type of energy, so long as you have the right way to convert them. Quite an interesting thing there. Now, one thing we haven't talked about are the units of energy. Okay, the units of energy is the joule. Okay, the joule. Now, the joule is defined as the amount, or sorry, 1 joule is equal to the amount of energy needed to lift a 100-gram apple, or 100 grams of anything, upwards by 1 meter. Okay, so 100 grams of anything, really shouldn't put apple, just anything. lifted up by 1 meter. Now, of course, that can be transferred into the amount of heat energy or the amount of electrical energy and so on. But that is the base definition of energy, and that's the definition that was given by Prescott Joule, who the Joule is named after for his work in this field of thermodynamics. Okay, which you'll read more about that in the reading that you do. That's basically all I wanted to go over with you. What I'll get you to do for the homework is please read in your books page 301 to 306. And if you could please do the questions 1 to 9 on page 307. Okay, we'll do that for our next class. You'll probably only have the one video this week as we get into the swing of things. But please let me know if you have any problems, and I can do either a follow-up video or a call with you to explain that. All right, thank you for listening.